In this video, we'll be talking about Newton's method. Newton's method is an approach in mathematics that allows mathematicians to make approximations of roots of functions using this formula that I will now write. Now this formula here is regarded as raphson's formula. Using raphson's formula. Now one thing we could do with this formula is we could evaluate the cube root of a number, say 10, without using a calculator. Now let's see how we do that. Say we want to evaluate the cube root of 10. Now the first thing we want to do is we have to write this in the form of a function such that y is equal to cube root 10. I can also go ahead and write this as y cube is equal to 10. Therefore y cube minus 10 is equal to 0. Therefore my function in general f of x is equal to y cube minus 10. The next thing you want to do is you want to take the derivative of this function here. That's f prime of x. Now f prime of x is 3y squared. Okay? If you understand the basic principle of differentiation, you just take the power to the front, subtract 1 from that power, and when you differentiate the constant, it gives you 0. Now from here, what we want to do is apply this formula here. Now we need to make an educated guess, which is going to be our x of 10 here. Now this equation literally allows us to make much reasonable or much approximated roots or function of numbers by using this formula. Here x of n plus 1 is equal to an approximation minus this ratio here, which is the evaluation of that function at the point of approximation divided by the evaluation of the derivative of that function, which is what we've done here. Now we want to apply that formula. So now to make a guess or to approximate what the cube root of 10 would be, we can easily get, since we know that the cube root of a number close to 10, like 8, is 2. So we could guess from there. So we could even use 2 as well. We say 2.1, but I feel like using 2 in this video session. So let's use 2. So now we can now use the formula x of n plus 1 is equal to our first guess is 2 minus the evaluation of our function at this point here. So this is our function y cube minus 10. So y cube is 8. 2. I'm just going to write that out. So it's 2 cube minus 10 divided by the evaluation of our function, the derivative of our function, which is 3y squared plus 3 2 squared. So that is equal to 2 minus, this will give us minus 2 because 2 is by 3 is 8, so 8 minus 10 is minus 2 divided by 2 squared is 4, 3 times 4 is 12. So the negative cancels out and becomes plus sign. So we have 2 over 12 is 1 over 6. Now if you press 1 over 6 in your calculator, you should have 0.1667. 2.1667. Now what we have to do is we're going to iterate and keep doing this like over and over till we get like the closest approximation to the actual value. Now just to be on the safe side, let's just calculate what the cube root of 10 is. And the cube root of 10 is approximately 2.15, so we know we are on track this way. So then there's only a small difference here. Let's do that again. It's 2.1544. So let's do that one more time to get a much closer approximation. Okay. So I'm sorry, I have to flip over. Now this time around, x of n is going to be the previous value, which is 2.1667, right? Now our formula is x of n plus 1 is equals to the previous term subtracted by evaluation of the function the x of n term and divided by the approximation of the derivative of the function at the previous term. So now that we know that, we're just going to apply that. So you have x of n plus 1, which is the next closest approximation, is going to be equal to the previous term, which is 2.1667 minus f, that's y cubed minus 10, right? So you have 2.1667 cubed minus 10 divided by 2.1667 squared. So we're going to need a calculator to do this. Should we go ahead and say that? So you have 2.1667 cube. Sorry. Try to keep 2.1667 cube is 10.1718 approximately minus 10 over, so we have 2.1667 squared times 3, that's 14.1 approximately. So here would be 2.1667 minus, this gives us 0.1718 over 14.1. Is that right? Yeah. So you have 0.1718 divided by 14.1. 2.1667 subtracted by 2.1667 minus 0.01218, that's 2.1545. Now when we pressed the calculator the other time, we found out that the cube root of 10 is approximately 2.15, and that's what we have here now. So we can just stop here. So we have evaluated the cube root of 10 without the use of calculator, using Newton's method. Now Newton's method can be used to a lot of other things as well. This example is just one aspect of it all. You can also use it to evaluate roots of actual functions, like iterating just like this. Now, just before we go, I would like to show you how this formula is derived as well. So let's say we have a function. Drawn this way. And this is f of x, or our y value. This is the x-axis. Now, we know that the root of this function is literally the point where it passes through the x-axis, right? And that will be here, right? So let's call this x1. Okay. Now, if we were to make an approximation or a guess, just like we did x of n value, remember, our guess could somewhere here, right? Now if I just fall somewhere here now, you just have an approximation, a y value on the curve or of the function here to be f of x1. Let's call this point x1. So the approximation will be f of x1, right? At this point. Now I can decide to draw a tangent. And if you do that, it will point on the x-axis. If you draw a tangent on that point, it will come straight down and point to a much closer approximation to the actual root of the function, right? So let's call this point x2. So I'm just going to divide that a, b, c. So we have a triangle like this, a, b, c, right? It's x1 minus x2. That's the distance here. And we have so now what we want to do here is look for the gradient of this line here. So the gradient is equal to the change in y value over the change in x value. Now the change in y value is literally the x coordinate here, the x value, the evaluation of our function at this point here, which is just f of x1. It's going to be f of x1 over the change in x value, which is x1 minus x2. So x1 minus x2, right? Now, being that this is a straight line, this slope or the gradient will be uniform throughout, right? Unlike this curve, the derivative here of the gradient here is different from the gradient here. Now, because we are taking the gradient here, we can assume, or we know that the gradient here at this point that is equal to this, the gradient of this line at this point, the gradient at this point is same throughout the entire line, and this gradient at this point is also the gradient of the derivative of our function of the actual curve at that same point. It's equal, they are equal. So we would have that the gradient of line AB is equal to the gradient or derivative at point A, or at f of x1, right? So what's our gradient? Our gradient is f of x1, change in y by change in x, and we said that is equal to the derivative at this point here. So we're just going to term that f prime of x1. Okay, so from here I can cross multiply, and we have that f prime of x1 dot, so this one, the dot is there to represent multiplication. It's equal to f of x1. Now I could divide both sides by f prime of x1, so that will go out. So you have x1 minus x2 to be equal to f of x1 over f prime of x1, right? Now if you note that the x2 is a much closer approximation, that's what we're looking for, right? We are looking for a formula that will help us get a closer approximation. This x1 is here, which was our initial guess. This is a much closer approximation which we're trying to get. So we're going to take this to the answer. So you have minus x2 is equal to f of x1 over f prime of x1 minus x1. So you literally just divide both sides by negative 1. So that leaves x2 equal to f. Sorry, since we divide both sides by negative 1, the signs will change, or in other words, you multiply both sides by negative 1. So the sign will change, and you have x1 minus f of x1 over f prime x. And our formula. Note that this is something as x of n plus 1. This is x of n. This is f. This is f of x of n, which is here. First guess over the evaluation of the function, of the derivative of that function at that point. So that's how Newton Raphson's formula is gotten from graph. So I hope you really enjoyed this video. Please subscribe to my channel if you did like what you just watched. If you want more videos on other topics as well, you can make some suggestions in the comment sections below. I'll be putting up more videos soon. Thank you very much, guys. Peace out.